Hello everyone, my name is Mikhail Maslov and I wish to tell you about the unique properties of silicon compounds that are called silicon polyprismanes. A few words about what are the silicon polyprismanes. Silicon polyprismanes, or according to the generally accepted classification Silaprismanes, can be considered as the layered dehydrogenated molecules of cyclosilanes, silicon rings, where M is the number of vertices of a closed silicon ring and N is the number of layers. For a large N, Polysilaprismanes can be considered as the analogues of silicon single-walled nanotubes with an extremely small cross-section in the form of a regular polygon. The slide shows the examples of silicon polyprismanes that are based on the regular penta, hexa, hepta and octagons. Hereinafter we use the following notation. N is the number of layers that make up the silicon polyprismane, M is the number of vertices in the regular silicon polygons, D is the refractive diameter of polysilaprismane, or the diameter of the circumscribed circle of the corresponding regular polygon. L parallel and L perpendicular denote the bond lengths between the silicon rings and inside the silicon cycle, respectively. It should be noted that the simplest representatives of polysilaprismanes, that consist of only two layers, were synthesized a long time ago. However, up to the present, unfortunately, there is no universal method for producing these molecular systems. Therefore, higher polysilaprismanes are studied exclusively theoretically, including computer simulation. The objectives of this work are to determine the geometry and energy of these compounds, their electronic properties, using the computer simulation in the frame of the density functional theory. To get an idea of the place of the silicon polyprismanes in modern technologies. We have analyzed a family of finite silicon NM prismanes with M is equal to 5, 6, 7 and 8, up to 10 layers, as well as rather long, infinite polysilaprismanes under periodic boundary conditions. Molecular structures of finite systems are displayed at the left side of the slide. It should be noted that for the lower M, that is equal 3 or 4, long systems with N is higher than 9 is not stable. Hydrogen passivation at the ends of polysilaprismanes was used to avoid the dangling bonds. In other words, all bonds in these structures are saturated. i.e., every silicon atom is sp3 hybridized and has 4 neighbors. Such finite oligomers were analyzed using the graphic subsystems dual NVIDIA Tesla K40 in the TerraChem program. For the finite systems, we used the hybrid functionals B3 LYP and PBE0 with Popel bases for the systems with M is equal to 5, 6, 7 and 8, and Dunning bases for the systems with M is equal 5 or 6. For the polysilaprismanes modeling under periodic boundary conditions, we used a corresponding supercell containing 4 elementary cells, i.e., 4 interconnected silicon regular polygons, C5 for the N5, C6 for the N6, C7 for the N7 and C8 for the N8 polysilaprismane. The examples of these supercells are presented at the right side of the slide. Calculations for the periodic systems were performed in the quantum espresso program using the PBE functional and ultrasoft pseudopotential for silicon. In this case, the distances in the XY plane were chosen over 14 angstroms to avoid the non-physical interactions between the object and its image. First of all, we optimized the geometry of our systems. In the case of periodic boundary conditions, the lattice parameters were also optimized, and determined the frequency spectrum to make sure that these structures belong to the local energy minimum. We are interested to know how the geometric characteristics of Polyprismanes change when every subsequent ring is added. The graph at the left side of the slide shows the change in the average length between the silicon rings with an increase in the effective length of Polyprismane. The average interatomic length was determined as the usual arithmetic average. It can be seen that after reaching 4 layers in the prismane, the bond length between the silicon rings does not change significantly, and in the infinite limit, it corresponds to the values indicated in the table on the right side of the slide. The effective diameter increases with the m growth, as it is expected. After that, we determined the binding energies of silicon polyprismanes, consisting of 2 to 10 layers. The binding energy was determined as the difference between the total energy of a silicon prismane and the sum of the energies of the isolated constituent atoms, referred to the number of atoms in the system. Polyprismane that possesses higher binding energy is more stable, and vice versa. The slide shows the dependence of the binding energy on the number of layers and the number of vertices of the silicon polygons. The binding energy dependence in a three-dimensional form is shown on the right. In general, it can be said that polyprismanes become more thermodynamically stable with an increase in their effective length. Thus, the formation of such type quasi-one-dimensional silicon nanosystems is energetically favorable. Of course, the kinetic stability of these systems requires additional analysis. Now we turn to the electronic properties of silicon polyprismanes. At first, we estimated the Homo-Luma gap. It is defined as the energy gap between the highest occupied molecular orbital and the lowest unoccupied molecular orbital. The Homo-Luma gap analysis is very important for the proposed use of the material in electronic applications as well as for the estimation of its reactivity. From the data presented on the slide, it is clear that the value of the Homo-Luma gap goes down with the increasing of the number of polyprismane layers n. A similar trend is predominantly maintained with increasing the number of vertices of a closed silicon rings M that make up the polyprismane. In the limit of the bulk system, Homo-Luma gap aims to the energy gap. In turn, the energy gap for bulk materials is a prime factor in determining its electrical conductivity. These values of the Homo-Luma gap are small enough to allow electronic conductivity. Thus, in the bulk limit, it is possible to transport electrons without any additional doping, with donor-acceptor atoms, or mechanical stresses. Thus, long polyprismanes can be referred to as semi-metals, or even metals. To understand a metallicity of silicon polyprismanes in detail, we analyze the band structure, density of electronic states, and electronic transmission coefficients of these nanostructures under periodic boundary conditions. One can see that the characteristic energy gap for the semiconductors is absent for all considered systems. On the contrary, the traditional for metals overlap of the energy bands containing the Fermi level is observed. To confirm the metallic behavior of Polysilaprismanes, we calculate the transmission coefficients of electron tunneling through the Polysilaprismanes. The calculation of transmission coefficients was made without the bias voltage. The polysilaprismane was partitioned into a device consisting of supercell containing 4 elementary cells and the left and right contacts that were presented by the same supercells as well. According to our calculations, the number of ballistic channels increases with the M growth. For example, C5 and C6 polyprismanes demonstrate 6 ballistic channels, while C7 and C8 polyprismanes demonstrate 10 ballistic channels, and therefore they possess an amount conductance of 6 G0 and 10 G0 respectively, where G0 is the conductance quantum. It should be noted that the electronic transmission around the Fermi energy of the common armchair metallic carbon nanotubes is sufficiently lower. Also, we analyze how the mechanical stretching and compression affects the electronic properties of gapless polysilaprismanes. The polysilaprismanes were stretched and compressed along their main axis by 10%. It was found that such mechanical deformations do not open the energy gap, so the metallicity of polysilaprismanes is resistant to mechanical deformations. However, we analyze the mechanical properties of silicon silaprismanes to investigate their response to both tensile and compressive strains along their main axis. We restrict ourselves to small strain values, not exceeding 4%, in order to maintain the system in the elastic region. For all considered polysilaprismanes, we estimate Young's modulus, that is given as the second derivative of the total energy E with respect to the strain divided by the equilibrium volume V0. Note that if the number of vertices of regular silicon polygons M that make up the polyprismane increases, the value of Young's modulus reduces. Thus, polysilaprismanes with smaller effective diameters are more resistant to the uniaxial compression and stretching under elastic deformation than the polysilaprismanes with larger effective diameters. The chemical reactivity indices or descriptors obtained for the silicon polyprismanes are electron affinity, ionization potential, chemical hardness and softness, chemical potential, electronegativity, and electrophilicity index. The chemical reactivity parameters are very important indices because they illustrate the reactivity and stability of a molecular complex. Electronic chemical potential characterizes the energy change when electrons are added to the molecular system, in other words, when the electron density changes. As one can see from the slide, the chemical potential dependencies on the number of silicon rings in the polysilaprismane have a sawtooth look. Electronegativity is an indicator of how favorable the molecular system is to the penetration of an electron charge. It is difficult to highlight the clear trend, but in general it can be said that the silicon polyprismanes with lower M and are more electronegative than the polyprismanes with higher M. In contrast, it is clear that the chemical hardness decreases with an increase in the number of layers N in the polysilaprismane for every M. So, when increasing the number of layers, the polysilaprismane is less and less hard. Chemical hardness characterizes the change rate of the electronic chemical potential with an electron density change. A hard molecular system is a system for which a small change in electron density leads to a significant change in the chemical potential. In this regard, the silicon polyprismanes are prone to electronic configuration changes. The analysis of electrophilicity reveals that, in general, it increases with an increase in the number of polysilaprismane layers. See the right figure on the slide. And furthermore, C7 and C8 polyprismanes are more electrophilic than the C5 and C6 polyprismanes at large N. On the other hand, the interesting behavior of electrophilicity index is observed at the number of silicon rings in the polyprismane N is equal to 9 and 10. So it is difficult to distinguish the clear trend of electrophilicity behavior at the bulk limit in the case then N tends to infinity. However, it can be assumed that at infinite length the silicon polyprismanes would be quite electrophilic. The extraordinary electronic properties of silicon polyprismanes, together with their structural and mechanical characteristics, make them potentially suitable in the various fields of next-gen technologies. Building the next generation of technological processes is impossible without the use of an improved material base. For example, the miniaturization of electronics inevitably leads to the using of appropriate semiconductor or metallic nanomaterials, which will provide in the future a significant increase in the speed of computing systems. Extended molecules of silicon polyprismanes may be the ultra-thin functional nanowires with controlled electronic characteristics and can be used in elements of computational logic. According to our studies, they have been found to be potentially good conductors. Encapsulation the metastable nanostructures, for example nitrogen chains, inside the high silicon polyprismanes can stabilize the latter, which will make it possible to obtain an effective high-energy material. Furthermore, high electrophilicity of polyprismanes indicates the possibility of including the charged ions inside their structure that might be useful in biological and medical applications as drug delivery systems. Also, silicon polyprismanes can be used for storing and transporting hydrogen instead of carbon nanomaterials traditionally offered in the literature for these purposes. Their conductive properties will allow one to use the polysilaprismanes as the elements of measuring equipment, for example, tips of a scanning tunneling microscope. In addition, the absence of free covalent bonds makes them insensitive to environmental pollutants or free radicals, which reduces the reactivity of the silicon needle, allowing one to achieve the atomic resolutions in the microscope. We have come to the end of our presentation. Thank you for your attention. We are always open to cooperation.